All right, welcome. We are in course 2 for Technology Fundamentals, our first session for the week on regression and descriptive statistics. Right, so regression and descriptive statistics today. Tomorrow, Varsha is going to go over NumPy as well as the debugging module. We'll pick up with statistics again on Wednesday, this time having to do with inferential statistics, and we'll finish out the week on model selection and validation. In this session, we will look at fitting data to a curve using regression. We will also look at using regression to make predictions for new data points by dividing our data into training and testing sets. This will be a short segue, and we're going to visit train and test set splitting more rigorously on Thursday when we get into model selection and validation. Finally, we will examine how much error we make in our fit and then in our predictions by computing the mean squared error. All right, importing some modules here. We should have seen all of these before. Pandas will have the alias PD, PyPlot, the alias PLT, and then we may not use it in depth today, but we're going to go ahead and import the interact module from IPWidgets. And then the main workhorse for today will be the sklearn module. We're going to look at creating linear models with linear model, splitting our data set into train and test set portions using train test split, and then evaluating our model with MSE and R2 score. We'll talk about each of those in a moment. Importing our wine data set from Kaggle. We'll remember that we saw this data set initially when we first were introduced to pandas. Looking at the shape of the data frame, so we have 6,497 instances or rows and 13 features or columns. We can look at each one of those numerical columns by doing df.describe. So this should all look fairly familiar. What is regression? Regression is the process of finding a relationship between dependent and independent variables to find trends in the data. This abstract definition means that you have one variable, the dependent variable, which depends on one or more variables, the independent variables. One of the reasons for which we want to regress data is to understand whether there's a trend between two or more variables. Let's take an example with housing prices. We can imagine the following. Envision a mixed data set of continuous and discrete independent variables. Some features could be continuous, like floating point values that indicate a location score or a housing condition. Others could be discrete, like the number of rooms or bathrooms. We could take these features and use them to predict an overall house value. This would be a regression model. So looking at the data set here, our last column, value, will be our y, our dependent variable, and all of the preceding columns will be our independent variables. Some are continuous, like this location or this condition column, and some are discrete, like the number of rooms or the number of bathrooms. To take this a step further, we can imagine that homes 1 through 10 are our training set, and so this is the data that we train a regression model on. And then we can imagine that we see some new instance here. The last row here just has the index new, and we're trying to predict its value based on the regression model. Linear regression fitting with scikit-learn. First exercise, rudimentary exploratory data analysis. What does the data look like? Remember how to visualize data in a pandas data frame from sessions 3 and 4. For every column, calculate the skew, the kurtosis, the Pearson's correlation with the dependent variable, and the number of missing entries, and organize this into a new data frame. Okay. Note, Pearson's is just one type of correlation. Another available to us is the Spearman correlation, which differs from Pearson's in that it depends on ranked values rather than their direct quantities. You can read more about it here. We have a little link talking about Spearman. All right. Let's look at this. We haven't talked about df.isNull before, so let's just look at what the raw output is. We see that it's a data frame of Booleans indicating whether at a given element in the data frame if we have a null value or not. If I sum this, I can then go down each column and count up the number of times I have a null. And that's what we're going to try to return here in the bottom in the following. So looking at part A, use df.method. Define the following 4 variables with the results from skew, kurtosis, core, and selecting for quality. All right, and then isNull. For isNull, you'll notice the return is a data frame of booleans. We just talked about this. We would like to simply know the number of null values for each column. Change the return of isNull using the sum method. All right, so let's go ahead and uncomment this. For skew, I'll do df.skew. And curt, I'll do df.kurtosis. Pearson's, I'll do df.core. All right, let's play around with this because we want to select for quality. Let's make sure we can do this just by doing core and then quality. All right, that looks fine. And also note it looks like the same output as .isNull.sum. So that's good. We want them to be of the similar form. So I'll just copy and paste that here. And then null, so df.null and then .sum. Make sure we don't get any errors. All right, .isNull. Looks good. Part B, on line 13, put these results in a list using square brackets and call pandas.dataframe on the list to make your different data frame. Store it under the variable name dff. All right, so we'll do, we'll also make this should be line 20, on line 20. So we'll do dff equals pd.dataframe and then a list, so skew, curt, pair, and null. So far, so good. Take the transpose of this data frame using dff.t, reassign dff to this copy. So it'd be dff equals dff.t. So there's the transpose. Set the column names. All right, so dff.columns equals skew. I have to put these in a list. Kurtosis. Pearson's underscore quality. Null count. Now return dff to the output so we can look at our handiwork. Nice, okay. All's is looking well. All right. Notice there's no skew, kurtosis, or Pearson's quality for the type column because this was a category. So it was dropped whenever we are doing those statistical operations on the numerical columns. Cool, I've gone ahead and repeated this exercise with the red and white wine types. So look, I'm doing all of the same stuff. I already saw all these steps, except I'm splitting my data frame into red and white wines. And then after I've split them and returned the summary on each one of them, on line 21, I concatenate the 2 data frames. When I use pd.concat, and feed it data frames whose columns have the same headers, I need to pass a key field to differentiate the 2 different data frames from one another because they have the same column names. Okay, so I'm going to run this, look at the result. We call this a multi-index data frame because there are 2 indices now, the feature names as well as the red and white wine types. There's a lot of numbers here, and anytime I see like a ton of numbers, I want to create a visualization around them so that it's a little bit easier to interpret. So that's what I'm going to do. Here I'm going to define a little visualization called myfig. And I'm going to plan on using InpWidget's interact method with myfig. So depending on what metric I want to view, I'm going to select these from the columns in the data frame. So I'll be able to select whether I want to view the skew, the kurtosis, and so on. And this is going to be a bar plot. So I'm going to return a horizontal bar plot, pin it to a figure that's 10 inches by 10 inches. Let's go ahead and look at this. All right, so by default, Interact selects the first column header as the viewpoint. We're looking at the skew. Something we'll notice is that for red and white wines, the skew of the residual sugar content is quite different between the two. If we lean on our knowledge, our prior knowledge of wines, we'll recall that white wine has a much larger sugar content. And it looks that as though while it has a larger sugar content, it has a more predictable sugar content as well, high and a little bit more normally distributed. And you can see that because the skew of the white wines is much lower than the skew of the reds. So looking at just these numbers here, it would seem that the red wines have a more abnormal or non-normal distribution around the sugar content. We can also look at kurtosis. We'll remember kurtosis is the degree of tailedness of the data. The chlorides and the sugars should really draw our eye here. Very non-normal distributions around chlorides and sugars. The quality, the correlation with quality. Of course, quality has a one-to-one correlation with itself. Another interesting thing here is the alcohol is positively correlated with quality, the alcohol content. So it would seem that the higher the alcohol content, the higher the quality ranking. Conversely, density very negatively correlated with quality. If we lean on our chemistry knowledge, the alcohol content has a very strong impact on density. If we've ever been to the bar and seen a bartender light a shot on fire, that is because they have very carefully poured the high proof alcohol on top of the other liquors or mixers, and it floats on top because it's less dense. So a higher alcohol content leads to a lower density. And if the alcohol content is positively correlated with quality, then it makes sense that the density would be negatively correlated. We see something similar with acidity here as well as chlorides. I am short on my wine knowledge to add some background to that, but presumably there's something dissolved in the wine that causes it to have a higher acidity, and this is negatively correlated with the quality. We can also look at the null counts. This will be important for deciding on how to deal with missing values. We'll talk more about how to deal with missing values when we get to feature engineering. We can look at the medians of each feature column, as well as the means. Means, look at this highest value is 140, median still 140. This is good. This shows us that there's not too many outliers in the data when mean and median agree with each other. All right, so we talked about chlorides, the residual sugars, the magnitudes and directions of the quality, how to improve this plot, what other plots would we like to see. Something I would think is with statistical data like this, we may want to see box plots perhaps of each one of the columns. Maybe KDEs to actually view the distributions. Looking at the chlorides, we saw that with chlorides you had a very high skew, much higher than any of the other columns, as well as a very high kurtosis. So let's just take a look at this. Recall that we can call the describe method on individual columns, and we're going to do that with the chlorides column. See that the mean is 0.56, pretty high standard deviation. And then the max value is 611, which is pretty high. It's an order of magnitude larger than the mean. So this is a little bit alarming. It's indicating that there's a pretty decent spread in the data here. We can look at the KDE. We see that a vast majority of the values fall below maybe 0.05, and then we have some high values that remain. Again, we're just going to kind of drill deeper, right? So we've used these aggregate descriptive statistics to identify feature columns that may be problematic in a linear model. And now we're going to look at the distribution as well as some other descriptive statistics on that column. And then we're going to actually look at the raw values. So we see here when we sort the chlorides column in descending order, we have a few values of 0.6, and then it drops significantly to the 0.4 range, 0.3, and then we get to some of the meat, the bulk of our data around 0.2. So we're just looking at these raw numbers because it will indicate to us things we may consider removing from the data set if we're looking to improve our model down the road. Okay, it's very important to do this sort of EDA on our data before we start modeling so we have some indicators for how we can improve the models should we so choose to. All right, moving on to visualizing the data set, motivating regression analysis. We can create a scatter plot of fixed acidity versus density of red wine in the data set using df.plot and see that there appears to be a general trend between these two features. All right, so I have acidity on the x column, density on the y column. And just looking at this data, they seem to be somewhat linearly correlated. Estimating the regression coefficient, let's pretend that for a moment we want to fit a line to this data. It looks like the density increases with fixed acidity following a line, maybe something like y equals mx plus b, where y would be the density, x the acidity, and m the slope, and b the intercept. To solve for this, the m and b in this equation, we need to compute a loss. All right. In linear regression, our goal is to minimize, in this case, the error between the computed values of positions, y_calc, and known values, y_exact. We want to, in other words, find a b and an m which lead to the lowest value of equation 2. We call this the residual sum of squares. Just reading this out, we have y_exact minus y_calc for every observation or instance, that is every row in our data frame. We square this difference and take the sum of all rows. Question, do we always want m and b to be large positive numbers so as to minimize equation 2? Just a little bit of a sanity check here. If we think about this for a moment, we don't actually really require any kind of constraint around m or b in this way, right? We can imagine depending on how y and x relate to each other, m could be very positive, it could be very negative. Same thing with b, right? B is just an indicator for where the line is crossing the y-axis, and we don't necessarily need this to be at any place in particular. Okay. So scikit-learn contains many functions related to regression, including linear regression. The function we will use is called linear regression. So the way I'm going to do this, and we'll find that the API for all the models in sklearn are extremely similar. I'm going to grab my linear model module and then grab the linear regression object in it and set it equal to the variable name model. And I like to do this with all my models. I just call them model just to be consistent. And then I'm going to take my density data and my fixed acidity data and map them to the variables x and y. The other thing you'll see here is I'm reshaping those columns, and we'll often do this with models in both scikit-learn and TensorFlow when we get to neural networks. And the reason for this is these models will often expect matrices, right? So matrices can have multiple values in 2 dimensions. In this case, we really only have 1 dimension, density for x and fixed acidity for y, but we're going to make them look like they could have more than 1 feature in each of those. And we're going to do that by just filling in a single observation on the 2nd dimension. So now we can look at this, and whereas before the shape was just 1599, that is 1599 observations, we now have a 2nd dimension where 1 observation is situated along that 2nd dimension, right? So if we want to look at this, do x.shape, oh, excuse me, we just do x. You see that in the 2nd dimension, we just have 1 observation, right? And that's indicated by the square brackets with, no comma separating multiple values. There's just a single value in that dimension, and that's where the 1 comes from. You can imagine if there were 2 features, there'd be a number here, comma, another number, etc. All right. What happens when we try to fit the data as is? Remember, I've called my model up above on line 2. It equals linear regression. It's a linear regression model, and I'm going to try to fit to x and y. We see we get an error. Input contains nan, infinity, or a value too large for data type float 64. So the problem here is that we have null values in our data frame, and this is telling us it doesn't know how to deal with those. There are a few options at our disposal for dealing with null values. We're going to take the very simple option today and just drop any row that has a null value in it in the density or fixed acidity columns. So exercise 2, drop null values. Let's look back at our data set description data frame above. What do we notice? What contains null values? There are several strategies for dealing with this, and now we're just going to drop them. Or we're going to take the simplest case and drop the rows with null values. For this templated exercise, you are going to complete everything in one line of code, but we are going to break it up into steps. So for each part, A, B, C, D, etc., paste your answer from the previous part to begin. Okay. Step A says select the density and fixed acidity columns of red. Make sure the return is a data frame. So I'll do red, and then density, followed by fixed acidity. And the return is indeed a data frame. Notice that I had to put the column names in a list because there's more than one. Now I'm going to take this and I'm going to copy it into the next step. Now use drop NA method on axis 0 to drop any null values. I'll do dot drop NA axis equals 0. That seems to have worked. Select column density. So we'll do density. And then step C, select the values. Okay, so now I'll do dot values. All right, so it returns an array now. Reshape the result with an empty second dimension using dot reshape and store the result under variable x. So it'll be dot reshape, and we'll do -1 to just replicate the initial dimension followed by 1. And this will be the variable x. And then for y, we'll do the same thing, except this will be fixed acidity, and we'll change this to y. Notice how I wanted to drop NA predicated on both of the columns density and fixed acidity, not just one or the other. And this is because I need the dimensions of x and y to match exactly. Now that we have our x and y arrays, we can fit using sklearn. So here I've already called x and y. And now we'll fit model.fit xy. We can extract the values of interest, so our m and our b, and look at their values. Cool. Exercise 3, calculating y pred. Estimate the values of y by using your fitted parameters. Hint, use your model.coef and model.intercept parameters to estimate y pred following equation 1. So we'll uncomment this and we'll just do y pred equals m times x plus b. Should work. Yeah, and so we get a line there, right? This is our prediction versus our actual, or our acidity versus our density rather, and our acidity on y. We can also return predictions directly with the model object using the predict method. So I'm going to do that here. Y pred equals model.predict. Cool. Run this cell. And now let's give explicit attention to these topics of model splitting. Starting with mean squared error. The plot in section 1, 2, 3 looks good, but numerically, what is our error? What is the mean value of the error, i.e. the mean squared error? So the MSE is going to be very similar to our residual sum of squares, except we are normalizing by the number of observations, right? And so this is so that our error doesn't scale, doesn't blow up the more observations we have. We don't want our error to be penalized by simply having more observations. So we divide by the number of observations. We can compute this directly with sklearn using the mean squared error method or function. See, our MSE is 1.68. Another way to measure error is the regression score, R squared. R squared is generally defined as the ratio of the total sum of squares to the residual sum of squares. Total sum of squares tells us the total amount of variance in our data. You'll see it's every observation, the actual y values, minus the average, that's what y bar here, y bar is the average of the data, squared, and then summed over all the terms. Right, so we're just looking at the variance, the deviation from any single observation from the population mean. The residual sum of squares is accounting for any variance not captured by our model. You can imagine if y-exact and y-calc are very close together, this would return 0. The square of 0 is 0 and the sum of 0 is 0. When they're very different, what this is showing is the amount of variance that's not captured by our model. When we take the ratio of the residual over the total, we're looking at what fraction of our model is not capturing the variance as a fraction of the whole variance in the data. So when we're doing a very good job, the residual sum of squares will fall towards 0. Of course, 0 over any number is 0, and 1 minus 0 is 1. So when our model is performing very well, our R squared will be 1. And then when our model is not performing very well, our R squared will fall towards 0. Something to note is that R squared can be less than 0, and this should indicate to us that our model is doing particularly poor. And there's probably something wrong with the way we've executed the training or the definition of our model. And the reason for this is, at the very least, our model should be able to predict y bar, right? You can imagine if y was not dependent on any of what we presumed to be the independent variables, we could still at the very least predict the average, the expectation of y. And so at the very least, SS residual should match SS total, in which case we get R squared equals 0. All right, so now we've just got a qualitative understanding of our bounds. Do we need a large value of the total sum of squares to minimize R squared? Is this something which we have the power to control? Again, just a sanity check here. We don't have any control over the total sum of squares. Right? This is just something dictated by the data itself. What we do have control over is the residual sum of squares, which is dependent on y calculated. All right, and we can take the R squared simply using sklearn. It'll do the mathematics for us. So this was regression, kind of a crash course on regression models. Let's talk about corollaries with classification models. Here now our error metrics are going to change. For classification tasks, we typically assess accuracy versus MSE or R squared, since we are dealing with categorical rather than numerical predictions. What is accuracy? Accuracy is defined as the ratio of true assignments to all assignments. For a binary positive-negative classification task, this can be written as the following: true positives plus true negatives over false positives and false negatives, as well as true positives and true negatives. T is true, F is false, P is positive, N is negative. Just as a quick example, we can perform this type of task on our wine data set by predicting on quality, which is a discrete 3 to 9 quality score. So I'm going to take my type of wine. Here's df type and the quality of wine as X. And again, we're just going to take a simple example here. So I'm going to call up the logistic regression blueprint from linear models in sklearn, set it equal to my new model name, and then fit on the train and test data. We can then look at the predicted classes based on the quality of the wine and get an accuracy. So 75% of our returned labels are the true labels. Again, we didn't really go into log regression or why I chose these two values to do the log regression. I just wanted to give us an example of how we would compute the accuracy score in sklearn. We'll have more dedicated time to this kind of model in the future. Beyond a single input feature, for those of us who are at all familiar with wines, we'll note that some of the features in the columns of this data frame may be indicative of the wine quality. This acidity of the wine, the dependent variable V, could depend on, for instance, potassium from the soil, unripe grapes grown in colder climates or reduced sunshine, pre-processing, other kinds of fermentation. So in our lab today, we will look at folding in additional variables in our data set into the model. Let's talk about this while we're together, multivariate regression. Let's now turn our attention to wine quality. So before we were talking about density and how it may be related to acidity, then we talked about how these other features may impact acidity, which should in turn affect the quality. The value we aim to predict or evaluate is the quality of each wine in our data set. This is our dependent variable. We will look at how this is related to the 12 other independent variables, also known as input features. We're going to do this just with the red wine data. So here we have the red data in a data frame called red. We're looking at the top 5 rows. Now we're going to perform linear regression with all input fields. For this example, notice we have a categorical data variable in the type column. We will ignore this for now and only work with our red wines. In the future, we'll discuss how to deal with categorical variables such as this in a mathematical representation. All right, so for now, we're just going to focus on the red wines and ignore the fact that we have a column with string values. So our features will be everything except the type column, as well as the density. We're going to predict the density. And again, looking at the nulls, we're going to get rid of some of these nulls before we actually fit our model. Here, we're doing that on X and Y. So X now will contain no nulls as well as Y. We can fit our linear model on X and Y and look at what the coefficients are. All right, so we've got this array now of coefficients. If we remember with the univariate regression, we just returned a number under model coefs. Here we have a list with 11 values. We have 11 values, and that's because we are regressing with respect to 11 independent variables, right? That's every column except for type and density columns. So now Y calculated is this summation over all the feature columns. We have 11 slopes or weights and 1 intercept. Right? We return the intercept with model.intercept. So we're just looking at these values here. And we can do a little conditional check. We want to check that the length of the feature dimension of our input array is the same as the length of the number of coefficients returned by the model. And if that's the case, we'll return all is good. The number of coefficients matches the number of input features. Right? We're just making sure that our notion of what the model should be returning is in fact being returned. Exercise 4. Let's evaluate the error by computing the mean squared error and R-squared metrics from equations 3 and 6. All right, so MSE, calculate the MSE using mean squared error. So I'll do mean squared error, look at the tooltip there, and it wants Y true returned first. I believe we just set this to Y, as well as Y pred. Let's make sure that these variables are what we define them above. So we have Y is the true, and Y calc, and I actually don't like the way this is called. We'll lowercase this for now. Y calc lowercase. So this will be Y calc. And R squared. This will be R2 score. And again, the true and the calculated. And we're missing a closed parentheses on these. There we go. We notice the mean squared error is a really low number. Maybe we want to change this. Let's change it to scientific notation. And I can do that by changing this F to an E. So now we get to see the actual value. Exercise 5, make a plot of y actual versus predicted. We can also look at how well the computed values match the true values graphically by generating a scatter plot. Generate a plot of y predicted versus actual using plot.plot. All right, let's test this out. So we'll do on line 4 here, we're just going to use out of the box nomenclature with pyplot. So we'll do x is going to be y, and then y will be y. Well, let's do x is y calculated, and y is y true, and we'll set ls equal to an empty string. Marker is going to be a period, and we'll set the alpha to 0.5, so you can actually see some of the overlapped points. Awesome. Much better than our univariate model, right? Having all those other variables really helped. All right, enrichment, splitting into train and test sets. So we're going to have a dedicated portion on train and test set splitting in model selection and validation. So we'll go ahead and skip this. And if we need to come back to it to make sense of some other stuff down in the notebook, we'll do so. All right. Other data considerations. Do we need all the independent variables? We'll discuss this on topics of inferential statistics in the next couple sessions. Can we output integer quality scores? Topics of non-binary classification checks are covered in weeks 3 and 4. Also left as an enrichment, discussing other algorithms. There are many other regression algorithms than the 2 we want to highlight here. Some of them are ridge, lasso, and elastic net. They differ by an added term to the loss function. Let's review equation to expand it to multivariate form. If we look at equation 2, remember this was y calculated, or y exact minus calculated. And now I'm just expanding it out to multivariate. So the second inner summation here is going to be over the input feature length, p. And we're just going to take the dot product of all our feature vector with our coefficient vector. That's what's happening here. We're multiplying by each element and taking the sum. For ridge regression, we add a regularization term known as L2, and that's this lambda summation here. So we have this coefficient lambda, and just the sum of our betas squared. For lasso, which stands for least absolute shrinkage and selection operator, we had an L1 regularization. So now it's the same thing. We have a lambda coefficient in front of a summation, but we take the absolute values of our betas rather than the square. The key difference here is that lasso will allow coefficients to shrink to 0, while ridge regression will not. Elastic net is a combination of these 2 regularization methods. We can train these models using, again, the linear model library in sklearn. And let's see, did I not define xtrain above? Let's just do x and y, and we'll predict on x. All right, so just out of the box, we have pretty good, you see everything's working. Coefficients and intercepts, so here's our coefficients, here's our intercept. You can do a scatter plot of this. We'll make x the calculated y. So up above we called it y calc test. We'll change this lowercase again. I prefer that since it's a vector. And y will just be y. Oh, and we'll import Seaborn. Seaborn. And this will be y and y, as well as y calc and y calc. Again, we'll change the MSE to be in scientific notation so we can see the actual error. Awesome. Very similar MSE to our non-regularized model. Initially, I had this as an exercise, and I've gone ahead and solved it for us so we can just go over the results. Exercise 6, tune hyperparameter for ridge regression. Use the docstring to peek into the hyperparameters for regression. What is the optimal value of lambda? Plot the beta values for lambda from the results of your analysis. So here I'm just looping through. I'm going to choose 10 different, 10 different splits of x and y. And again, we're going to talk about this methodology of train test split in a later module. So we'll just take it at face value for now. We're then going to iterate through 109 or 108 different values for lambda. Remember, lambda is the term in front of the penalization component of our loss function. So the higher lambda is, the more we're going to penalize our model for having high beta coefficients. So the higher lambda, the more our model will want to reduce beta. And so it forces the model to choose values of beta that negotiate between these two sides of the loss function. On the one hand, we want y calculated and y exact to match, and on the other, we want to do this with as low and as few of beta terms as possible. And this is why we call it regularization, because it helps us choose which features we should include in the model. All right, so I'm going to loop through there. And now I'm just doing some pre-processing. Got to import NumPy. We'll have a module tomorrow on NumPy. And then plotting the results. And so indeed, as we move from left to right, we're increasing lambda. On y, we're looking at the value of our beta coefficients. And as we increase lambda, we can see these move towards 0. All right. Last thing we do here is we can look at the performance of the model with respect to lambda as well. As we increase lambda in this case, our scores seem to be doing better. It looks like we could increase lambda a little bit more, right? If we're just looking at this score here, we may consider increasing lambda to see if this flattens out at some point. All right. We have some additional regression exercises left as an enrichment. Problem 1 is number and choice of input features. Load the red wine dataset and evaluate how the linear regression predictions change as you change the number and choice of input features. The total number of columns in X is 11, and each column represents a specific input feature. Estimate the MSE. We have an example on using the first 5 features, how you would do this. And you can walk through this yourself. Just a little bit of an exercise here. Problem 2, type of regression algorithm. Try using other types of linear regression methods on the wine dataset. The lasso model and the elastic net model, which are described by these 2 modules in linear model. You can read more about them here and here. And then questions to think about while you work on this problem. And you can read through this as you perform the exercise. And that's it.